Okay, good afternoon everyone. My name is Gerard. I'm going to talk about a new concept that we're introducing into multi-agent systems and an architecture, also a design pattern of how to develop a multi-agent system using this concept. But to understand this concept, I need to just quickly go over those two concepts. The first one, what is a holonic system? The formal definition, that it's a system where a single element called a holon serves as both a whole and a part simultaneously, and it was coined by Arthur Koestler in 1967. But a practical example of this, one that we can all understand, is the structure of the universe. So we all live on a planet. Take a bunch of planets and they form a solar system. Solar systems form a galaxy, cluster, superclusters, and eventually it will lead to the universe. An important thing to notice here is that every single element that you see here is a system on its own. It has its own unique, distinct properties and behaviors, but it forms part of a bigger system, except for the universe, which might form part of the multiverse if we believe in that theory. But how does that translate to multi-agent systems? It's actually very simple. We take a very big agent and we subdivide it into smaller agents, and they subdivide into smaller agents, and so this process continues recursively. And each agent, as it gets smaller, becomes more context specific and it solves a smaller problem. So a holonic system is great for taking a very big problem and subdividing it into smaller problems. So that's holonic. What is quantum superposition? It inspired me to try and implement it into multi-agent systems. So the formal definition is quite lengthy. It's the hypothesis that a quantum particle exists in multiple quantum states simultaneously. The act of observing a quantum state called the wave function causes the quantum particle to collapse to a single measurable quantum state. That's quite lengthy. So this most simple example that I could find of a quantum superposition is when we look at an electron. An electron actually has a spin, an upward spin or downward spin, negative, positive. When we make absolutely no effort to observe what direction those electrons are spinning, on a quantum level, they are spinning in both directions simultaneously. So that quantum system is existing in all quantum probabilities. I know it sounds very weird, it sounds awkward, but it is scientific fact. There's a lot of evidence that supports this. But as soon as we do make an observation, so we want to determine in which direction this electron is spinning, it collapses to a single measurable state. So it will either spin upwards or it will spin downwards. So when we observe, it collapses. When we don't observe, it exists in all states simultaneously. And the act of observing is called a wave function. So we'll get to how that actually incorporates into the architecture in a little while. So if we take the three terminologies, holonic, superposition, and multi-agent systems, we came up with an architecture called Splinter. So what are the objectives of Splinter? First of all, it's a development architecture and also design pattern to create multi-agent systems. So it's something that we can create multi-agent systems with. It focuses heavily on holonic agent architectures, as we'll see in a few moments. And the most important, that it's an architecture for runtime pluggable multi-agent systems. So we want to be able to provide you with an architecture where we can plug in and plug out agents without disrupting the entire system or an agent or agents, and we can do all of this during runtime. So how do we want to achieve this? We want to achieve this by introducing the Splinter design pattern. So to get to know the Splinter design pattern, the first thing, we just have to know some basic terminology. So whenever we have an agent that is made out of other agents or forms part of another agent, we call that a nano agent. And any agent that does not form part of another agent, so it hits the end of that holonic hierarchy, we call that a tera agent. The second principle in the Splinter design pattern, and it's probably the most important one, is that the design of every agent starts out as an interface. We don't have class implementations. The Splinter design pattern goes against that. So every single agent starts out as an interface. And because of that, we have two core interfaces, the nano interface and the Terra interface. So every nano agent must inherit from the nano interface, and every Terra agent must inherit from the Terra interface. And this allows Splinter to enforce some form of predictability and behavior over all the agents. So to explain to you how the whole superposition principle comes into play, I'm going to give you an example. So let's say, for example, we have a nano agent. It's called the repository nano agent. And this agent has a very simple task. It's to store and retrieve data. That's it. And because it's an interface, it can have multiple implementations. So let's say, for example, this interface has 4 implementations. The first one, it's a database agent, so it stores it in a conventional DB. Uses cloud storage. It has one that uses offline storage, maybe like a CSV file or an Excel file, or one that uses the memory of the actual nano agent itself. Now, the question that you should be asking yourself is, how does Splinter know which implementation to use during runtime? There are 4 implementations, so how does it know which one to use? And this is where the superposition principle comes into play. We have what is called the collapse algorithm. Now, the collapse algorithm is actually outside the scope of this literature and the presentation, but I am going to give a very broad overview of how it actually works. So the collapse algorithm will give you an implementation of the interface, but it does so by using a collection of n-wave functions. N-wave function stands for nano-wave function. These n-wave functions, they perform a number of observations. They measure things, look at conditions, and they say that for this interface, I will give this implementation. But the collapse algorithm uses a collection of them. But we can implement our own distinct n-wave functions. We can have one or many, and each of one of them can be distinct. We can have a very simple one that has a one-to-one mapping that says, for this interface, I will use this implementation. We can have one that uses AI techniques, maybe like neural networks, reinforced learning, evolutionary algorithms. One that consults another agent to determine it, or we can have one that consults an external system or web system. But the bottom line is that the collapse algorithm, at the end of the day, by using a collection of observations being made, causes that interface to collapse to one of the implementations that are available. And that brings us to our next important principle in Splinter, and it's the recollapse principle. It's probably the most important one. And to explain that, I'm going to use this example that we've been talking about. So let's say, for example, our collapse algorithm made observations, and it says the best implementation is the cloud storage. Why? Because there is internet connectivity. Now, let's say, for example, that internet connectivity drops. And then another observation is made by an n-wave function that says we should actually use the memory storage because there's no internet. And then it replaces that nano agent implementation. And this is actually the important part of Splinter, because Splinter allows any nano agent, doesn't matter where in that Holonic architecture it is, to replace any nano agent with another nano agent during runtime. So we don't have to disrupt anything, we don't have to bring it down. On a native level, Splinter allows us to plug in and plug out at runtime. But for this memory agent to exist, we obviously must have the observation that enough memory exists. What if we don't have enough memory? Well, then maybe we can go to an offline implementation. And then let's say over time, another observation is made by some kind of an n-wave function. Internet comes back on, and we restored back to the cloud storage implementation. So the Splinter architecture with the Splinter design, at the end of the day, when we look at the holistic view, it's a Holonic architecture of agents made out of agents, but any of these nano agents, any of these smaller agents, we can replace them at runtime with any other implementation and that's a native function or functionality of Splinter. So how do we want to apply Splinter? We want to apply it by extending the existing BDI model. What is the BDI model? It's a very old model, but very popular, very well proven, where we try to model the intelligence of an agent, and we try to give it human-like and human cognitive reasoning abilities. And it's made out of 3 concepts, very easy concepts to understand. Beliefs, desires, and intentions. Beliefs is what does an agent believe about itself, other agents, the world it resides in, what are the rules and constraints. It has desires, a collection of objectives that it wants to achieve over time, and that obviously can change. And it has intentions. How do I actually achieve those objectives and goals that the agent believes in? So what we want to do is we want to extend this BDI model using the Splinter architecture and the Splinter design pattern. So we start out with our Terra agent there, and that Terra agent embeds another agent called the knowledge agent, which is a nano agent. And so this encapsulates the entire knowledge nexus of this agent. But from a perspective of the BDI model, that employs another agent that represents the beliefs. That one entails another agent that reflects the desires. And that nano agent can produce another agent that's the execution plan. So the execution plan is what it executes to achieve its desires and objectives, and that again is made out of steps. So the 2 most important things to take note here, the first being that every single component here is an interface. So that means that there are multiple implementations for each of these interfaces for different scenarios or different environments. And the second is that except for the first component, every other component here is a nano agent by the terminology, and therefore we can plug in and plug out any of these components during runtime, and we can give it a completely different, we can give it different reactions to different dynamics and conditions and so forth. So this is how we want to give it the term Holonic superposition intelligent and multi-agent systems, because of the Holonic architecture and trying to incorporate the superposition principle into how we determine which implementation should be used. So the next step is how do we actually want to apply this extended BDI model? And a fun way was, I thought, RTS games, real-time strategy games. What is an RTS game? An RTS game is a game where players attempt to defeat opposing players by building very powerful armed forces. Players train armed forces by purchasing technologies, conducting research or training armed forces, usually using rare resources provided within the RTS environment. So I'm sure that we've all played some form of an RTS game. It's basically where you build an army, you upgrade your army, you improve your army, you try to overthrow your opponents using some kind of a rare resource like gold, crystals, oil, wood, depends on the game. But there are modern day challenges in RTS games when it involves AI. So when we put AI in RTS games, we usually are faced with 2 predicaments. The first one, the AI is just too predictable. The AI becomes too repetitive, and the gamer can easily exploit that repetitive or predictable behavior of the AI. Or at the other end of the spectrum, it just becomes too difficult. The AI is just too good. And this lowers the gaming experience that a player experiences during their RTS game. It's either too easy or too difficult. But there's a lot of research literature out there that says if we take the BDI model and we combine it with the artificial intelligence in games, we actually get more human-like behavior, because that's the whole goal of the BDI model. So there's a lot of research literature that actually supports this, but there's not a lot of research literature that tries to incorporate the BDI model into RTS, artificial intelligence. So we took it upon ourselves to take Splinter and our extended BDI model and combine it with RTS, and we come up with a real-time autonomous superposition strategy war, for short, RIPSAW. So what is RIPSAW? RIPSAW has a number of objectives. The first one, it's a platform for autonomous agents to compete. So RIPSAW has its own rules of engagement, what to do, what it can't do, and it's only allowed for autonomous agents to participate. So they compete against one another, and the one that survives last is the winner. It tries to, or it does incorporate the Splinter BDI model as its nexus of intelligence. We'll have a look at that in a few moments. But the most important is that it attempts to provide more human-like behavior, because that's one of the challenges. How do we want to do this? Well, we have a new interface called a RIPSAW commander that extends the Terra agent. And the RIPSAW commander component implements its own BDI model. So it has its own knowledge interface, its own beliefs, and its own desires. Believing about what is right, what is wrong, what is weak, what is strong. So this is all good and well, but there's one major flaw with this architecture, and that is potential information overload. If you have to think about everything that AI has to do in RTS games, such as resource gathering and planning, defensive and offensive planning, long-term strategic planning, short-term tactical planning, development and research strategies, and threat analysis of enemies. And it might actually be much more complex than other RTS games. So taking all of this into consideration, cramping it into one little component that will over-engineer it, overcomplicate it, and it's probably almost impossible to engineer and implement. So how do we try to solve that? We try to solve it by implementing
You have 5 more minutes, please wind up. No?
Advisors. So an advisor is a nano agent that addresses very key specific areas of interest within the RTS environment: military, economic, offensive, defensive, and research. So they address very specific things in the game. So how does the advisor actually work? Well, the advisor itself has a BDI model again. It has a belief about what is strong, what is weak, what is good, what do I want to do. It has its own set of objectives and beliefs of what it wants to do. And it does this by creating something called a recommendation. So the recommendation says what the advisor wants to do, not necessarily how, but what it wants to do. And it submits this recommendation to a commander, and the commander again uses its own BDI model to evaluate this recommendation. So it will either reject it or it will approve it, but it can partially approve it as well. And if it does approve it, then the advisor will execute it using its own intentions module from its own BDI model. So the commander employs a number of advisors. These advisors tackle very focused areas within the game. They all have their own BDI model. But because we have the concept of collapse and recollapse, as I talked about earlier, we can have advisors being plugged in and plugged out for different scenarios. So let's say, for example, we are in a very defensive mode. We need to go in defense, then we can plug in and plug out any component, doesn't matter how big or how small, that still addresses key responsibilities, but that is tailor-made for defensive purposes. Well, let's say, for example, we're running out of resources, so it's very limited. We can plug in and plug out advisors, still addressing their key responsibilities, but that's tailor-made for that specific situation where there are limited resources. So last page, we have a Splinter Architecture, and we have the Splinter Architecture is made out of Terra agents. And this Terra agent, from a perspective of RIPSAW, is a commander. And a commander has its own BDI model made out of smaller components again. And the commander then employs a number of advisors, and they all have their own components and BDI models. So this clearly shows the Holonic architecture of agents employing agents, and as it gets smaller and smaller, it becomes more specialized and solving smaller tasks. And with a superposition principle, that every single component here that in red, by native functionality or native support of the Splinter architecture, allows us to plug in and plug out without disrupting any part of the system. So I believe that this is an architecture and approach that allows us to build multi-agent systems where we can plug in, plug out, not only the intelligence, but every single small component that you wish with another implementation based on the observation of internal or external dynamics and observations. Thank you for listening, and I'll take any questions.
In fairness, let's give chance for maybe one or two short questions, and then we'll start the discussion. Any questions?
I have
Yes.
some questions.
Yes.
I write papers on countermeasures. You don't explain and present the relationship between the component of the Holonic.
So the Splinter design pattern does not expect you to define that relationship, or doesn't have a default relationship. So the designer or the person implementing that that agent will have to define that relationship explicitly. So in this regard, I'm only referring to the Holonic architecture of an agent and being able to replace those agents, but there's no Splinter itself does not restrict to a default relationship. That is up to the designer of the multi-agent system. Because one of the objectives of Splinter is to have an architecture for you as programmer and developer to design your own multi-agent systems.
I have the same question about the succession, the sequence of belief, desire, and intention. I think it's not a sequence, it's more circular, multi-relationship.
Yeah, so the diagram that I showed there was just to actually show the flow of how intelligence will probably work. But the actual implementation in the architecture and in the PhD that I'm doing, they are very interconnected with one another. So one can influence the other. You can set up those relationships again and within the Holonic architecture if you should wish. But yes, I do agree that within, on a more detailed level, they are circular. One influences the other.
Any more questions?
I have a question more from an engineering perspective, because your approach, I think, relies very much on the separability of all the problems into partial problems which have no intercoupling. Okay?
Mm-hmm.
And this is, I think, a side effect-free programming is a paradigm in computer science. And this supports this kind of strategy. However, in engineering, if you do something, you have n-1 side effects, because, for example, if you previously built your fuselage out of an aluminium alloy and you switch for lightweight material purposes to carbon fiber or plastics in general, then suddenly lightning might become an issue. So I am wondering, when you apply such an agent problem-solving approach to a real-world problem, whether you can manage to clearly define the classes of problems to which you can successfully apply, because you need to have this side effect-free problem decomposition, because otherwise you run into...
So that's one of the disadvantages of a Holonic approach, is that the complexity can very quickly become quite complex, because you're going into agent and agent and agent, and as you said, from an engineering point of view, we don't know what those side effects are. But because of the Splinter design pattern, with that regard, is that if I wanted to let me just go back. So with a design pattern, because everything is an interface, I can actually stop the Holonic architecture right there, and I can remove those two. And because an interface at the end of the day has a very, I think people sometimes struggle with it. It's when you define an interface, it has to be what does the interface do, not how does it do it. So if you want to make this interface into hundreds of smaller pieces, that is up to the designer. But if you as a person only want to use this single component and make it big and clunky, then you can do that. So, but I do understand your problem with
That's
that.
an a posteriori answer. But if you use this as a learning system, you need an a priori answer. So I think you would need a mechanism which detects that there is a failure in separating the problem into two independent parts. Because this is what happens always in engineering when airplanes were flying below Mach numbers. Everything was fine, and then suddenly when they had larger engines, airplanes went faster, and then the wings broke, and it took us a couple of accidents to find out that there was a coupled error elasticity problem.
Yeah, I understand your.
This is a remark.
I'm just thinking that it's the one that you didn't go into much detail, but correct me if I'm wrong, you probably could do sort of a imperative non-functional side effect full implementation. It all depends on how those n-wave functions work. So if your n-wave functions, you make them as what they call a stateful function or a functionoid or a functional object, basically a function that remembers things about previous state, basically has its own mutable state that it manages. Then they could store things about the failures of decomposition or various other issues in it. It would mean that the n-wave function, because I think the impression I got was that you wanted them to be really simple mappings between observations and likelihood of a particular implementation being selected. But you could make a big messy n-wave function that handles all of the state management if you needed to.
Yeah, I think the whole idea of Splinter is that every single component is not hard-coded. That if you want to, you can swap in components and you can add one n-wave function or hundreds of these things. And you can, like Dr. Colter said, that we can actually implement that does other types of observations. So it's not limited to these types of observations. There can be anything type of observation that you wish to plug in. So the whole idea of Splinter, myself as a professional developer, I'm not a full-time academic, is we have to sometimes compensate for when a network goes down, and these things do happen. And there's no architecture that actually provides low-level functionality for this, and so this is the whole idea that nothing is set in stone. You can do it as you wish.
Okay, thank you very much.